Assalamu alaikum wa rahmatullahi wa barakatuh. Chapter 7 Work and Energy. By studying this chapter, we will learn the following goals: work, energy, potential energy, kinetic energy, and conservative and non-conservative field. First of all, work defined by the method of transferring energy to the system by force and causing it to displacement. Here, this photo shows transfer of energy from wind to the electricity. Now we can beginning with the definition of the work. The work can be defined as the force multiplied by distance multiplied by cosine angle. The angle is defined between the force and the displacement. Here we have three cases for the work in this equation. First, if the theta equal to 0, so we have maximum work, or theta equal to 180, we have negative work, and if theta equal 90, we have 0 work. Also, if the distance equal to 0, we have 0 work, and also if the force is 0, so the work is 0. Now we can define the work by another definition. If we have force F and parallel distance to the force, we can calculate the force by multiplying the magnitude of the force times to the distance parallel. If there is an angle, can multiply it by cosine this angle. We note that the work is a scalar, not a vector quantity. Also, we note that the force is vector quantity multiplied by the displacement, also vector quantity. Now we have the following examples for the work. Now, if this atlas holds up the earth, he does work or not? He doesn't move, so the displacement is 0, so the work is equal to 0, because the work defined by the force multiplied by the distance, and here is the distance equal to 0, so the force multiplied by distance equals 0, so the work is 0. Now, he doesn't do any work. Another example, this person does work when he pick up the tray only, because we have the two components, the force and displacement, but not why he carries it around the room. He doesn't any work, because the distance is not 0, but the distance parallel is 0. So when he pick up the tray, he make work, but when he walk in the room, doesn't work, because the distance parallel is 0, so the work is 0. We have two examples for calculation the work. Example 1, a man cleaning a floor pulls a vacuum cleaner with a force of magnitude F equal 50 Newton at an angle of 30 degrees with the horizontal. Now calculate the work done by the force on the vacuum cleaner, as the vacuum cleaner is displaced 3 meters to the right. We can solve this example by the definition of work. We can define the work by equation. The work equal the force multiplied by the distance multiplied by cosine 30. Where is this 30? Is the angle between the force and the displacement. By calculation, for these simple calculations, we can get the work equal 130 joule. The other example 2. A particle moving in the xy plane undergoes a displacement given by r equal 2 in the direction of x plus 3 in the direction of y in units of meter. As a constant force, F equal 5 in direction x plus 2 in direction y by units in Newton acts on the particle. Now calculate the work done by the force on the particle and its direction. We can solve this example by the definition also of the work. The work can be defined by the force multiplied by the displacement and multiplied by cosine theta. Now we have the magnitude of the force equal square root of the two components of the force, and take the root mean square, we can obtain 5.4 Newton. And the magnitude of the displacement, we can take square root of the square of 2 plus square of 3 and take the root mean square of the result. We can take, given the magnitude of the displacement, r equal 3.6 meter. Now from the definition of work equal force multiplied by distance equal by vector product 16 joule, and we can calculate the direction by the equation of work multiplied by cosine theta. We need now the theta. The direction or the theta equal the inverse cosine of the force dot product with the displacement divided by the magnitude of the force multiplied by the displacement. You can check these calculations and we have the direction about 35 degrees. Please do this calculation by yourself. If we have applied different force, for example, not constant force, here the force is variable. So we can calculate the work by this form. If the particle move from x initial to x final, he make an area with rectangles of delta area, delta A equal f of x multiplied by delta x. So we calculate the work by the area under the curve by the integration from the initial xi to the x final for f of x dx. So we can calculate the work by the area under the curve. By the definition from Newton's second law equal F force equal m multiplied by acceleration. By this definition of work and a little of calculus, we can deduce the work equal the change in kinetic energy, or half mv square. This little of calculus here, this is the network, the integration from x initial to x final. The force here is Newton's second law, mass multiplied by acceleration, delta x. So we can find the integration of mv dv by half mv square. We note that F is the vector equation and the work we know is the scalar equation or scalar quantity. Now the work is a change in kinetic energy. That's to say, or called work energy theorem. When the work is done on the system and the only change in the system is in its speed, as we show the previous slide. The net work done on the system equals the change in the kinetic energy of the system. We can check units again. The kinetic energy half mv square, mass in kilogram and v in meter square per second square. Now work, force multiplied by displacement, also Newton by meter, or kilogram multiplied by meter over second square multiplied by m. So we have the same units, so we have the same quantity, kinetic energy and also the work. Both units equal joule. Now we have example of the kinetic energy for the earth and automobile or oxygen atom. Now calculate the kinetic energy for the earth. The mass of earth is approximately about 6 × 10⁻24 kilogram, and it is speed around the sun about 3 × 10⁴ meter per second. Now calculate the kinetic energy equal 2.6 multiplied by 10⁻33 joule. The other example was the automobile at 65 miles per hour. It is mass about 210 or 2000 kilogram. It is speed about 29 meter per second. Now calculate the kinetic energy equal 8.4 10⁵ joule. The last example, the oxygen molecule in air. It is mass equal 5.3 10⁻26 kilogram, and it is speed about 500 meter per second. So we can calculate the kinetic energy equal 6.6 10⁻21. Now we can calculate the work done by the gravity, where is the force equal mg. So the work, as we defined, force multiplied by distance, the force equal negative mg, and the displacement is the change in height between the initial and final, or start and end. So the work done by the gravity equal negative change in mgh, where is the m is the mass and g gravity acceleration and the h is the height. Now we have example. If we lift this book from the table or the ground, we can calculate the work done by this lifting book. The gravitational potential energy equals the work in due to gravity force equals the negative change in potential energy, which is called mgh. M is masses and g acceleration of gravity, and the h is height. So the work due to gravity equal the negative change in potential energy due to gravity. Now, if the gravity is the only force doing work, we can define work energy theorem by the negative change in potential energy, mgh, equal to the change in kinetic energy, half mv square. So the change in potential energy plus kinetic energy equal to 0. So the potential energy plus kinetic energy equal constant. This is the conservative energy. And thank you. This is the first part, and see you soon again with the next part of this chapter 7. Thank you for your attention.